Hello everybody. My name is Levon, and today I'll be presenting the astronomy problem of the day. I recently wrote a research paper that I'm going to be presenting at Stanford Online High School's astronomy research seminar on, Hubble's constant and non-conventional ways of looking at Hubble's constant. In other words, let's get started with this problem of the day. So we have two parts. The part A says the universe is believed to be expanding at 70 kilometers per second per megaparsec. Why is it reported in units of kilometers per second per megaparsec? So to start off, let's look at an analogy. So we have J in this analogy, who's standing in a field at the center, and then we have Peyton, who's 100 meters away from J, running at a speed of 50 meters per second away from him. Then we have Failing, who's 200 meters away, running away at a speed of 100 meters per second. Alessandra, 300 meters away, running away at 150 meters per second. And now it asks Xander is 400 meters away from J, and he's also running away. How fast do we think he's going? So you can kind of already sense a pattern. Like for every 100 meters, their speed increases by 50 meters per second. But the best way to solve kind of problems like these is to look at it visually. So we can pull up, kind of make a graph like this of the recessive velocities as a function of how far away they are from J. And then here are the respective points. You have Peyton, Failing, and then Alessandra, all in this line. And then here you have Xander. So the quickest way you can probably get his, how fast is he running away, is to just look at the y-axis. But if you want to know how fast someone's running away, basically at any distance away from J, so not just like on these, like where you see this grid, it's preferable that you find the slope of this type of graph. And that's just going to be y2 minus y1 over x2 minus x1, which results in 0.5 meters per second per meter. And then also note that you're also going to be dividing the units. So here you see the y-axis meters per second over the x-axis meter. So you get the slope of 0.5 meters per second per meter. And to see how fast Xander is running away from, again, he's 400 meters away from J, and if you're going 0.5 meters per second every meter, it's just going to be 400 times 0.5, which is 200 meters per second. And in universal terms, you could say, and this is based on observations, that for every megaparsec of distance you go away from the Earth, galaxies are going to be receding 70 kilometers per second faster. And that's what's called Hubble's constant, this 70 kilometers per second per megaparsec. And you can see kind of a similar graph, except it's based on, distances from the Earth of galaxies and the respective recessive velocities. So the next kind of question to ask is, does this mean we're at the center of the universe? So if you just look at this diagram alone, you might think that because, everything's running away from J. But here's point of view becomes really important, because let's look at this situation from Payne's perspective. For him, you can see everything's running away from Payne. So really, you can't just assume that because everything's running away from you, you're at the center of the universe. And here you can actually see this diagram shifted to Payne's perspective, and to him, he's at the center of the universe. So you can't really assume too much about that. Now, as for the question, which is essentially what do these like kilometers per second per megaparsec mean? Essentially, this explains it pretty well. Not as you go further away from Earth, you're going to have galaxies receding faster and faster. So that kind of means that as the universe is expanding, the expansion is also accelerated. And that's kind of the meaning of Hubble's constant here. Here we have the raisin bread model, which is essentially that analogy you just saw, but in 3 dimensions. So as you bake like a raisin bread cookie, each raisin in the cookie is going to move apart from the other raisins. And if you have 2 raisins on like separate ends of the cookie, they're going to separate much quicker than if you had like two raisins like in the middle. They're going to separate much more slowly. So this is called the raisin bread model, and it kind of models how the universe has expanded since the Big Bang. Now, one of the very interesting questions we look at with Hubble's constant is the age of the universe. So in the analogies, if we look at it from the analogy, we can ask, when did this mad race begin? So that's essentially when J told everyone to start running. And if we assume that all of their velocities are constant from the beginning, well, we see that Payne's running away at a speed of 50 meters per second, and he's 100 meters away. So that would kind of intuitively, you'd say, well, it would take 2 seconds for him to run 100 meters. So you can kind of infer that everyone started running 2 seconds ago. And the really interesting thing about that is that 2 is the exact inverse of the slope right here, the slope of the recessive velocity as a function of distance graph, which is 1/2 essentially. And notice that 2 seconds and 1/2 meters per second per meter are inverses in their dimensions as well, because you can see the meters are going to cancel with each other and you're just going to get 1/seconds. So you can kind of infer that if you take the slope of a recessive velocity as a function of distance graph, and then take the inverse of that, you can get the time where the actual race started, or when the Big Bang happened, the age of the universe essentially. So we know Hubble's constant, 70 kilometers per second per megaparsec. Let's find the age of the universe for the universe. The best way to do that is, again, of course, 1/Hubble's constant, but you're going to have to multiply by a lot of different, you're going to have to convert a lot of the units to be uniform. So you're going to convert megaparsecs to parsecs, parsecs to kilometers to cancel with this other kilometers term, and then seconds to years to get the age of the universe in years. Again, these are all conversion factors, and you're going to get a term that has a 1/years. So eventually, when you all simplify it out, the age of the universe, you get 13.9 times 10 to the 9 years. So basically, the inverse of the Hubble's constant is going to be the age of the universe. And again, the Hubble's constant is pretty much the rate at which the universe is expanding. So now let's go on to part B. The question asks, here, let me get my video thing out of the way. The critical density, rho sub c, of the universe is the density at which a particle's kinetic energy due to the expansion is equal to the magnitude of the gravitational potential energy. If the density of the universe were lower than this critical density, expansion will continue indefinitely, like you see with this green sloped graph. On the other hand, if the density of the universe were any higher, it would recollapse upon itself with this orange curve. And then if the universe has uniform density and expands linearly with velocity v equals Hubble's constant, that's h sub 0, times the distance x, show that the critical density is equal to this below. So we essentially want to find the situation where we have this blue curve, this kind of flat universe with the critical density. So first let's start out with the equation they give us, v equals h sub 0 times r, which is the distance. You might ask, well, if we have kinetic energy and gravitational potential energy, how is Hubble's constant and this universal, the gravitational constant going to come in, and critical density and all that? Well, we're going to be actually going to plug in this V equals H sub 0 times R into the kinetic energy equation. So you know that kinetic energy is 1/2 mv squared. So plugging in for V, you're going to get 1/2 m Hubble's constant times R in parentheses squared. So now we figured out the kinetic energy that we're going to have to set equal to the gravitational potential energy. So now let's find the gravitational potential energy. Well, the first thing we need is the mass, specifically the mass of the universe. And this is where we can, introduce this critical density variable. You probably know that density is equal to mass over volume. So the mass is going to be equal to the density times the volume. In other words, mass is equal to 4/3 pi r cubed times the density, critical density, rho sub c. And then you might ask, well, why is the volume 4/3 pi r cubed? But the universe is going to be expanding like a sphere in all directions. So you're going to have to use the volume of a sphere and then multiply it, of course, by the critical density. So now we have an equation for mass in terms of the variables we need. So now we can plug that into our gravitational potential energy equation, which is negative the gravitational constant times little m, probably the mass of the particle, times big M, the mass of the universe, over R. Note that there's a minus here. And then, substituting in for M, we get this kind of ugly thing, but you're going to see a lot of things are going to start canceling. So in order to get this like critical density where the universe neither continues to expanding or then recollapses on itself, you're going to have the kinetic energy of the particle directly be balanced with the potential energy of this particle. And then another mathematical way of saying that is that the kinetic energy added onto the potential energy is going to have to be equal to 0. And we already have the two equations for kinetic energy and potential energy. We can substitute in. And then from here on, it's kind of simplification. We see that the little m's, the mass of the particles, are going to cancel. We're going to have r squareds canceling. And we're eventually going to result in this critical density is equal to 3 times Hubble's constant squared over pi times the gravitational constant. So I think that concludes the problem of the day. Thank you.